Hello students, this is Professor Chalai, and in this video we're going to look at chemical stoichiometry and gases. As always, you can follow along with our Chapter 9 workbook. By the end of this video, you should be able to perform stoichiometric calculations involving gases. Let's get started. So earlier in the semester, we talked about stoichiometry, where they often, always require a balanced chemical reaction, and we stated that the stoichiometric ratios or stoichiometric coefficients, where they're not written, it's just implied that it's 1, gives us the ratios that these ratios between the number of moles that is needed to carry out this reaction. So for example, in this here we have, whoops, not to erase. We know that for this reaction to proceed, 1 mole of carbon monoxide will react with 2 moles of hydrogen gas to form 1 mole of methanol. And so if we can figure out the number of moles of one substance, we can figure out the amount of mole of any other substance within that chemical reaction. So the same is true when we're dealing with gases. So before, when we're talking about number of moles, we got those number of moles either from converting mass to moles or from converting concentrations to number of moles. So that's when we're dealing with solid or solution phase reactants and products. But with gases, we can find number of moles, as we learned earlier, from using our ideal gas law equations, right? PV is equal to nRT, and here it tells us number of moles. So similarly, as we did with stoichiometric calculations earlier in the semester, once we find number of moles of one of the gas, we can use that ratio to find number of moles of other properties in the reaction, and then find whether we're required to find the number of mass of that substance or any other property of that substance once we have the number of moles. So let's look at number 31 as an example. In number 31, we have methanol, which in this case is a gas, is synthesized using carbon monoxide and hydrogen gas. It tells us that 1 mole of carbon monoxide reacts with 2 moles of hydrogen gas to form 1 mole of methanol. So the question is, what volume in liters, so that's our question, I'm just going to put a question mark there, of hydrogen gas, so what volume of hydrogen we're looking at a temperature of 355 Kelvin, so they give us a temperature in Kelvin, that's good, and a pressure of 738 millimeters of mercury. We want the pressure in atmospheres, so this is 0.971 atmospheres. I'm going to assume that we know how to do that conversion quickly now. Is needed to synthesize, we have 35.7 grams of methanol, CH3OH. Okay, so that's what we're given. We're asked to find the volume of a gas. So PV is equal to nRT. We know the pressure. We know R, we know T. We always know R, and we know T. So if we can find the number of moles of this gas, then we can find the volume. But in order to find the number of moles of hydrogen, which is the gas they're asking for, what volume of hydrogen gas? So in order to find the number of moles of hydrogen gas, we need to first find the number of moles of one other component in this reaction where we actually know something more about it. In that case, that component is methanol. We know the mass, we can easily figure out the molar mass. So the molar mass of methanol, we should have had lots of practice doing this, so I'm not going to show you how. Well, let's do it. It's what, 12.01 for carbon, it's 1.01 for hydrogen, and there's 4 of them, and it's 16.00 grams per mole for oxygen. That comes out to be 32.05 grams per mole. So now that we know the molar mass, we can figure out the number of moles of methanol, right? And that we take, to do that, we take the mass, 35.7 grams. We divide it by the molar mass, 32.05 grams per mole, such that the grams cancel out, and we should get 1.11 moles of methanol. But in all stoichiometric calculation, this is the number of moles of methanol. We need the stoichiometric ratios to figure out the moles of the other substance, in this case hydrogen. So we see that for every 1 mole of methanol, we get 2 moles of hydrogen. So let me go over here. So the moles of hydrogen, I'm using N because this is a gas and we use it in the PV is equal to nRT equation, is going to be the moles of methanol, which is 1.11, nice number, moles of methanol. And the mole ratio is for every 1 mole of methanol, we get get 2 moles of hydrogen, so that the number of moles of hydrogen is 2.22. That's simple math. Okay, so now we know the number of moles of hydrogen, right? We can find the volume, so let's write that. The volume should then be equal to the number of moles times of hydrogen times R times T divided by the partial pressure of hydrogen. So let's punch in numbers. 2.22 moles times 0.08206 moles times liters liters times atmospheres. There we go. Divided by moles times Kelvin. The temperature they told us was, where are we? 355 Kelvin. And all of that divided by the partial pressure, which we calculated to be in atmospheres 9.971. Not 5, 1 atmospheres. Okay, let's see what cancels out. Moles with moles, Kelvin with Kelvin, atmospheres with atmospheres. We're left with liters, which is exactly what we wanted. And the liter, I think I got 6.66 liters. So let's go over this again. It's a stoichiometric calculation, but involving gases. We know how to get number of moles from mass. We know how to get number of moles from concentration. I believe we did a few more, I can't recall. Now we know how to get number of moles from pressure and volume and temperature. Basically, the quantities of a gas, the properties of a gas that we have. Okay, so let's do number 32. We have a different reaction happening here. Pause the video and try to see if you can figure it out on your own, and then we'll go over it together. Okay, so in this reaction, we have silver oxide decomposing to give us silver and oxygen gas. So here they give us the liters of oxygen, so that's our volume, right? 4.58 liters. Give us the pressure. Pressure is 745 millimeters of mercury, which we need in atmospheres, so this comes out to 0.980 atmospheres. They give us a temperature in Kelvin. That's nice of them. And by them, I mean me. I'm just joking. Okay, and they want us to know the mass of silver oxide. All right, so in order to find out silver oxide information in stoichiometric with stoichiometric data, we need to find out the number of moles of one of these two other components first. We don't know anything about the silver, so let's work with the oxygen. We know the pressure, temperature, and volume. We can find the number of moles. So let's do that. Number of moles of oxygen from PV is equal to nRT. The number of moles should be PV over RT. That's the one that we're going to be using a lot with stoichiometry, so it would be nice to have it written nicely somewhere. So it'll be the PV over RT, and the pressure is 0.980 atmospheres. The volume is 4.58 liters. R is always 0.08206 liters times atmospheres divided by moles times Kelvin. And the temperature is 308 Kelvin. So that gives us, let's see, liters with liters, atmospheres, kelvins, kelvins. I love when things cancel out nicely. We're left with number of moles. But how many? 0.178 moles of what gas are we working with? Oxygen. But we want moles of silver oxide. So the moles of silver oxide, Ag2O, is we have 0.178 moles of oxygen. And the mole ratio here is for every 1 mole of oxygen, we get 2 moles of silver oxide. So the moles of silver oxide is just 0.178 times 2. What does that come out to? 0.356 moles. Okay, now that we know the moles, they're asking for the mass. And we know how to do that easily, right? We just use the molar mass, which let's do that. The molar mass of Ag2O. I'm assuming that we all know how to do this very quickly now. It's 231.74 grams per mole. And so the mass of Ag2O will be the number of moles, 0.356 moles, multiplied by the molar mass, 231.74 grams per mole, such that moles cancel out, and we're left with a mass of 82.5 grams. So, like all stoichiometric reactions, calculations, we calculate the number of moles of the known compound first, use the mole ratio to calculate the moles of the unknown compound, and then use whatever conversion we need to find what they're asking from the unknown compound. Let's try number 33. If you haven't yet, please pause the video, try it on your own, and then we'll go over it together. So number 33, same reaction. So let me just clean this up because it's the same reaction in case we need to write on it. What's the mass? So we're looking for the mass of Ag2O again. So, okay, it's going to be similar. To form 388 mils of oxygen, so that's our volume. It's 388 mils, but we need this in liters, so it's 0.388 liters. There's a pressure, 734 millimeters of mercury, but in atmospheres, this is 0.966 atmospheres. And the temperature is 25.0 degrees Celsius. But to convert that to Kelvin, we need to add 273.15, right? So this gives us, I believe, what, 298.2 Kelvin, right? The first decimal place. Okay, so we have pressure, volume, temperature. We already know we can find a number of moles of, what gas are we working with? Oxygen. So number of moles of oxygen, what did we say it was? PV over RT, right? So P is 0.966. Let's make it a little bit bigger so I can write a little bit neater. Atmospheres. V is, where are we? 0.388 liters. R is always 0.08206 liters times atmospheres divided by moles times Kelvin. And temperature is 298.2 Kelvin. So for cancellations, we got liters with liters, atmospheres with atmospheres, kelvins with kelvins, and number of moles of oxygen turns out to be 0.0153 moles. Okay, but we want the number of moles of the unknown. So moles of the unknown, Ag2O, will be 0.0153 moles of oxygen. But for every 1 mole of oxygen, we get 2 mole. Well, is that true? Yeah, 1 mole of oxygen, we get 2 moles of Ag2O. I was just going off of memory there. But if you're not sure, always check back the equation. So this should give us 0.0153 multiplied by 2, I believe gives us 0.0306 moles of Ag2O. Okay, so that's the middle step. First step, get the moles of the known compound. Second step, get the moles of the unknown compound. And then third step, find the unknown quantity of the compound that the unknown compound we're working with. In this case, it's the mass. So the mass of Ag2O should be the number of moles, 0.030, is that 6? I think that's a 6 moles. And to convert moles to mass, we just multiply by the molar mass. We calculated that earlier up here, I believe. Well, we didn't. I assume you knew what it was. It's 231.74. 231.74 grams per mole. Moles cancel, and we get a mass of Ag2O, 7.10 grams. Again, same steps. The only difference now is we're dealing with a gas. First, find the number of moles of the known. Second, find the number of moles of the unknown. Third, convert that number of moles into whatever interesting property we're looking for. Okay, let's try number 34 now. If you haven't, as always, please pause, work it on your own, and struggle through it, and then we'll work it out together. Okay, here we have hydrogen reacting with oxygen to form water. And the question is, how many grams of water form when we have 1.24 liters of hydrogen gas? So there's our volume right away, 1.24 liters. The gas is hydrogen, so we're looking at this as our unknown. Sorry, this is our known, and how many grams of water? So the mass of water is our unknown, right? We have 1.24 liters of hydrogen, at STP. Remember what STP was, right? This is why we need to remember what STP, standard temperature and pressure, NTP, normal temperature and pressure are. So standard temperature and pressure, the temperature for the STP part was, temperature was 20 degrees Celsius, which comes out to 293.15 Kelvin, right? You add 273.15 to it. Pressure for standard temperature and pressure, easy, 1 atmospheres. Okay, so yeah, temperature, pressure, volume. We can find number of moles. Number of moles of oxygen will be PV over RT. Pressure is easy, 1 atmosphere. Exactly 1 atmosphere, so it's not 1 sig figs, it's infinite sig figs. Volume is 1.24 liters. R is 0.08206 liters, atmospheres, moles, Kelvin. Temperature is 293.15 Kelvin. And we know it should cancel out, but I love doing it anyway. Cancel, 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 cancel. We get number of moles of oxygen as, what does the calculation come out to? Let's see, 0.0515 moles. That's the known. But, so now let's find the number of moles of the unknown, which in this case is water. So moles of water is 0.0515 moles of oxygen, right, O2. And then let's use mole ratio. 1 mole of oxygen to 2 moles of water. So 1 mole of oxygen to 2 moles of water. So the moles of water is, let's see, I multiply all of that by oh, sorry. This is number of moles of hydrogen. There we go. I thought something seemed weird. There we go. Hydrogen, because it's 1.24 liters of hydrogen gas. I don't know where I was getting oxygen from. So in this case, for every for every 2 moles of hydrogen, we get 2 moles of water. So the mole ratio here is just 2 moles to 2 moles of hydrogen. So basically, this is just the same number. So number of moles of water is 0.515 moles. Yeah, I'm not sure why I was thinking of oxygen. It completely reacts with oxygen. They don't tell us any other information about the oxygen. Okay, so now we have the number of moles of water. We can find what they're asking us for, which is the mass of water. Before we do that, we need to find the molar mass of water, which I've used so many times. I can tell you it's 18.02 grams per mole, but if you didn't, you know how to find it, right? Okay. So the mass of water, right, will be number of moles times the molar mass. That moles cancel out, and this should give us 0.928 grams. If anytime any of my calculations are wrong, please let me know. I could punch in incorrect numbers. It's been known to happen. Okay, so there we have it. Same stoichiometric calculation. First step, find number of moles of the known. Second step, find number of moles of the unknown. Third step, find find the interesting property of the unknown that we're looking for. Okay, one more for practice. Number 35. Let's try that. It might be written a little bit differently, but let's try it. So we're asked to find how many liters of oxygen. So we're asked to find the volume, right? Liters is volume. It's at STP, which means the temperature is 293.15 Kelvin, and the pressure is 1 atmosphere. And then the mass of H2O is 10.5 grams. So right away, we should be thinking water is our known, right? And oxygen is our unknown. So let's first find the number of moles of our known compound. So moles of water. We know the mass, 10.5 grams. All we got to do is divide by the molar mass, which we just said in the previous question was 18.02 grams per mole. And so this comes out to 0.583 moles of water. Okay, now we need to find the number of moles of our unknown, our oxygen. Looks like for every 2 moles of water, we get 1 mole of oxygen. So moles of oxygen, or we should just write N with an O2 there, should be the 0.583 moles of water times the mole ratio is 2 moles of water to 1 mole of oxygen. So we're essentially dividing by 2, and so that should give us 0.292 moles of oxygen. Okay, now that we find a mole of the unknown, let's find the quantity that we're interested in, which is the liters. So how do we do that? Well, let's see. PV is equal to nRT because it's a gas. If you want to be a little bit more careful, it's actually pressure of oxygen, because it's there might, well, is there another gas in there? Yeah, there's hydrogen. So partial pressure of oxygen times the volume is equal to number of moles of oxygen times R times T. Okay, we know number of moles, we just calculated it. We know R always. We know T because it was at STP, which means we know the pressure as well. Yeah. Okay. So let's find the volume. The volume should be number of moles times R times T divided by P, which means that we have 0. What is that number for number of moles? 292 moles for N. R is always 0.08206 liters times atmospheres divided by moles times Kelvin. And the temperature was 293.15 Kelvin, right? It's STP. All of that divided by the pressure of just 1 atmosphere. For unit cancellations, we get moles, moles, kelvins, kelvins, atmospheres, atmospheres, and liters is what we end up with, which is exactly what we wanted. So, punch all of those in a calculator, I get 7.02 liters as a volume. All right, same steps as all stoichiometry problem. The only difference is we can convert from moles to different quantities using different things, like I mentioned earlier. We just need to keep all of these things straight in our head. All right, to close off this section, let's look at number 36, and let's think about it. We have nitrogen and hydrogen reacting to form ammonia according to this equation. 1 mole of nitrogen plus 3 moles of hydrogen to form 3 moles of ammonia gas. Now the question is saying that if we keep the volume constant, so wherever this reaction is, it's in a closed container that's not changing in size, and nothing else is added, right? What happens to the total pressure? So let's say nitrogen is going to be purple. No, not purple. Let's say nitrogen is going to be blue. Nitrogen is very blue. Oxygen will be, sorry, I say oxygen. Hydrogen is red, and when they react, they form purple ammonia. Okay, so let's think about this. If you think you have the answer, please go ahead and do so. But let's look at the box, right? So we have nitrogen, there we go, reacting. And what color was, and the hydrogen was red, okay. We have this reacting, what's the ratio? 1 to 3, so I need less. Let's say we have 4 nitrogen, which means we need 12 hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And eventually we form, so what I did here was basically 4 nitrogen plus 12 hydrogen, just to sort of mimic this ratio here of 1 to 3, right? 1 to 3, just to show you visually what's going on. We form 3, so that would be multiplied by 4, we'll have 12. I'll form 12 ammonia, right? So let's draw 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I couldn't keep the sizes the same. Okay, what do we think happens to the pressure as this reaction happens, is carried out? Well, we talked about how the pressure is related to the number of moles, and on the left-hand side, right, we have total number of moles being greater than on the right-hand side. So if I remove these number of dots and just replace it with the with the mole ratios, right? We start with 4 moles of reactants to form 3 moles of product. Remember that PV is equal to nRT, or if you want to separate it out into gases, P of one gas is equal to number of moles of one gas. P of the second gas, let's call it B, is equal to number of moles of the second gas, right? So what that means is the pressure is directly related to the number of moles. Why? Because the volume we said is kept constant, R is kept constant, and we could assume that T is also kept constant. So the pressure and the number of moles are directly related in this example. So if the number of moles go up, the pressure should go up. If the number of moles go down, the pressure should go down. But as this reaction happens, the number of moles go down, so the pressure should decrease. All right, so that's just some things to think about. I think in general chemistry 2, if you do take it, we'll do a lot more studying about like directions of reactions and what happens in gaseous and other types of reactions. But that will bring us to the end of stoichiometry in gases. It's the same kind of questions that we've been doing since the middle of the semester with stoichiometry, right? The only difference here is we now have a gas, which means we need to use the ideal gas law. But the principle is always the same. Find the number of moles of your known compound, use that and the mole ratio from your balanced chemical equation. I think I went too far up. Like this, use your balanced chemical equation to find the number of moles of your unknown compound, and then use that number of moles to find whatever property they're asking for. All right, we'll stop here. In our next video, we'll talk about diffusion and infusion of gases. I will see you then. Bye.